The system is composed by two disks of mass moment of inertia J1 and J2, and they are mounted on a shaft. The two segments of the shaft have rotational spring constant of K torsional 1 and K torsional 2. For J1 equals to J sub 0 and J2 equals to J sub 0, and K torsional 1 and K torsional 2 equals to K torsional, we like to find the natural frequencies omega 1 and omega 2 and the vibration modes of the system. We take moment of each of the rotational disks along the axis of the shaft, and then we have that the moment created by the rotational spring 1 will be the constant of the spring times the rotation of the disk. The moment created by the second segment of the shaft will be the relative rotation between the two disks times the constant of that spring. And that's equals to the mass moment of inertia of the disk 1 times the angular acceleration. These two equations can be written in Mattins form as following. We have a mass matrix multiplied by the acceleration vector plus a stiffness matrix multiplied by the displacement vector. The matrix as follows. Since the J1 is equals to J sub 0 and J2 is equals to J2 sub 0, we have a diagonal mass matrix, and we have the matrix for the stiffness takes this form. The second step is to find the eigenvalues of the problem by finding the determinant of this matrix, which is the stiffness matrix minus lambda times the mass matrix. That gives us the characteristic polynomial, and which is a second order polynomial that we, using the quadratic equation, we can find the roots for that polynomial. And those roots are the eigenvalues of the problem, which are also the square of our natural frequencies of the system. Now that we have the natural frequencies of the system, the next step is to find the vibration modes. To find the vibration modes, we will introduce the eigenvalue that we found into our matrix and find this vector. These two equations represent the same equation, therefore we will have to find a relationship between these two amplitudes. If we give the value of 1 to the amplitude of the first disk, we can find how much the second disk will move for the first vibration mode. And that gives us the first vibration mode. We do exactly the same for the second eigenvalue, which represents the second natural frequency. We include this value into our matrix right here, and we solve the equations, and we give the value of 1 to the amplitude of the first disk, and we find how much the second disk will move for that vibration mode. Now we have the two natural frequencies and the two vibration modes. These modes look like that graphically. It means that if the disk 1 moves 1 unit, then this 2 will move 1.7808 units in the same direction. It means it will rotate in the same direction. And in the second mode, if the disk 1 rotates 1 unit, the disk 2 will rotate in the opposite direction, 0.2808. If we have two 1 degree of freedom system composed here with a segment of shaft and a disk of mass moment of inertia J sub 0, this will be the natural frequency of this system. And if we have a disk that has 2 G sub 0 as mass moment of inertia, this will be the natural frequency. If we take these two 1 degree of freedom systems and compose them in a 2 degree of freedom system like this one right here, we still have two natural frequencies, but as you see, those natural frequencies will be different from the original ones. So it's very important that we have to understand that when we have a 2 degree of freedom system, we have to calculate the new natural frequencies. The same happened with a translational system. If we have a 1 degree of freedom system, and we compose it in 2 degree of freedom system, the natural frequency will be different from the original ones.